So welcome to the Week 1 Math 2419 weekly review. In this one, we'll just kind of get started. I believe you mostly covered a lot of review things from last semester, but today we'll be talking about vectors first just in 2 dimensions in the plane, then we'll start talking about them in some higher dimensions, and we'll finish up the session with some notes about the dot product. So we start off some vectors in the plane. So if you recall, a vector is, in simplest terms, a directed line segment. It is a pair of coordinates. We usually write them in component form, x, y, and we say that it has two things: magnitude, which is how long it is, and direction, which is, well, the direction. And if we were to sketch out a vector, we usually sketch it as an arrow like this. And we conventionally say that vectors start at the origin and go to the point x, y. So this would be the vector x, y. And this should all be review. But this is essentially how we write out vectors. Let's see, if we want to define the magnitude, we can, of course, use the Pythagorean theorem to say the magnitude or length of the vector, which we say is, which we write like this. So if v is our vector, we denote it using the double bars on each side. We could say that the magnitude is the x-coordinate squared plus the y-coordinate squared. And then we take the square root of that, just like the Pythagorean theorem tells us to. And there are a few different things that we can do with vectors, a few different operations we can perform on them. So let's say we have two vectors. U is u1, u2, and v is v1, v2. Then first off, we can add two vectors. So if we did u plus v, well, then we just add their separate components. Oh, that should be u1 plus v1, sorry about that. u1 plus v1, u2 plus v2. Just like you would expect. We can also multiply by a scalar. And so if c is just some constant, then c times u would be c times u1, c times u2. See, a couple of important things is if we take the magnitude of the vector cu, well, that would just be the absolute value of c times the magnitude. We have such magnitude should always be positive because it's just a length, and we can't exactly have a negative length. However, when we're adding vectors, we have to say that the magnitude of the combined vector, u plus v, is always going to be smaller than or equal to the magnitude of u plus the magnitude of v. And this is something very famous called the triangle inequality. And the reason being is if you draw out a triangle, you can let two of its sides be vectors, like so. And then this third side would end up being the sum of those two vectors. So if this is u and this is v, this would be u plus v. And you can see that if we took the length of one side and add it to the length of the other side, well, the longest it could be would be exactly equal to the sum of both the vectors. It can't get any longer, but it can, of course, be shorter. So that's why we have this inequality. Let's see. We'll go over one other definition, and that's going to be a unit vector. And a unit vector is simply a vector with length 1, length or magnitude of 1. And we'll go ahead and do an example. Let's say we have a vector v equals to -5, 12. And we want to find a unit vector in the same direction as v. Or in other words, we need to find a vector that's of length 1 and points in the same direction as v. Well, the easiest way to do this is to find the vector v divided by the magnitude of v. Because when we take a vector has two components, magnitude and direction. So if we divide by the magnitude, well, we're dividing by essentially the same length, so that's going to give us a length of 1. But because this vector v already has a direction, then we'll be preserving that direction when we divide. So first off, we need to find the magnitude of v, and to do that, we use the Pythagorean theorem. And we get the square root of 25 plus 144, which is the square root of 169, which is equal to 13. So we simply need to take this vector, -5, 12, and when we divide by 13, we're essentially multiplying by 1 over 13. And from our previous rules, we know how to multiply a scalar into a vector. So then our unit vector would be -5 over 13. We just multiply the 1 over 13 in, 12 over 13. And that would be our unit vector in the same direction as v. Make sense? Cool. Let's see. One other thing to note is the difference between v and magnitude of v. When you have just v, this is a vector, but this is a scalar, so this is not a vector. So you could say magnitude of v times v, and this would actually work. You would just multiply whatever this number is into v. And that's just an important distinction to make, because a lot of the times people tend to get confused by, oh, am I working with a vector or am I working with just a number? So make sure you pay attention to when things are vectors versus when they're numbers. And there are a couple of standard unit vectors, and those are I, which is the unit vector in the x direction, j, and occasionally you'll see vector k. Actually, you'll see it more frequently as the semester goes on, but that's the unit vector in the z direction. And again, if we were to plot these on a coordinate plane, unit vector I would just be like this, right along the x-axis, and j would be right along the y-axis, and they would both have a length of 1. K, of course, would be along the z-axis. And if you were working in 3 dimensions, these last two coordinates, I and j, would both be 0, of course. But you might see these on occasion, and those are just your standard unit vectors. Okay. Let's see. Next, we'll move on to vectors in space, just because basically everything you do with a vector in a plane, you can do to a vector in space. And They're just typically vectors in space are not easier to work with, but more applicable to everything. So for a vector in space, all the same rules apply, except your vector has maybe more than just two components. In fact, it can even have an unlimited number of components. Like you could have a vector that has eight slots for numbers instead of just two or three. I believe in 2419 you'll mostly just see three or two, but it is helpful to know that you can have a lot more than just those three coordinates. But still, finding the magnitude of a vector is exactly the same. You just use the Pythagorean theorem, except in this case, it would be x squared plus y squared plus z squared, and then you take the square root of all that, or potentially even in general, just the square root of all the terms added up. So you square every term, add it up, that should be a squared, and then take the square root of that. That's how you find the magnitude of a vector in space. Similarly, you can add and subtract vectors the same way you can on the plane. You can multiply by scalars just like we saw on the plane, and all the other properties just follow along, same as in the plane. So it's really not that complicated. Let's see. We'll talk about parallel vectors now. So if we have two vectors, u and v, but we say that they are parallel if u is equal to some constant times v. So for example, if we have u equal to 5, 7, and v is equal to negative 15, negative 21, well, then we can say that u is equal to negative 1/3 of v, so u is parallel to v, because we found this constant right here. And if we wanted to represent that graphically, well, we say that vectors are parallel if they lie on the same line. And when we multiply a vector, really all we're doing is we're stretching it. That's not what I want to do. Really all we're doing with the vector is we are stretching it, or compressing it. So if we said twice this vector that I've drawn right here, it would just be stretching it by a factor of 2. So it would look like that and just expand along the same line. And if we multiplied it by basically every number, we could end up at any point along this line. So as long as the vectors have the same direction, we can say that they're parallel, and that's really all that this is checking. Any questions so far? Okay. Cool. And I believe all of this should be a review from 2417. So let me know if I'm moving too fast or anything, or you want me to clarify anything. Let's see. We'll go ahead and move on to the dot product, because that is, I believe, probably the more important thing to know. You've probably worked with vectors quite a bit by now, but the dot product might still be a bit unfamiliar to you, depending on how you use it, how you've used it in the past. And the dot product is one way that we multiply two vectors. So if we have two vectors, u and v, there are actually a couple of different ways we can multiply them. We've got the dot product, and we've also got the cross product, which you will learn about later. But the dot product is the most common way of multiplying two vectors because it works on vectors in any dimension as long as the vectors are the same size. And when I say that the vectors are the same size, I mean they have the same number of coordinates. So we have an x comma y comma z vector. Well, we can multiply that by, we can take the dot product of any other vector that has 3 coordinates. But we couldn't take the dot product with the vector that has, say, 2 coordinates. Anyway, the dot product is essentially calculated by saying u1 v1 plus u2 v2 plus u3 v3. And that is if u is equal to u1, u2, u3, v is equal to v1, v2, v3. And all we're doing is we're just multiplying each coordinate and then summing them all up like so. And one important thing to notice is this gives you a scalar, or a regular number, not a vector, as output. There are a couple of properties of the dot product that are helpful. First off, it is commutative, and that means that we can switch the order. Say that u dot v is equal to v dot u. It is also distributive. So u dot v dot w, u dot v plus w, that's what I mean, is equal to u dot v plus u dot w. If we multiply by a scalar, well, this one's a bit weirder to think about, but still not that bad. Basically, since our output is a scalar, we can think about just multiplying this top equation by c on both sides, and then it just depends on where we put this constant on the right-hand side. That's all that's going on here. Vector, so a zero vector is a vector that has 0 for all its components. And we take the 0 vector dot any other vector, then that gives us 0 as a scalar. And lastly, there's one other property I want to talk about, and that is if you take the dot product of a vector with itself, you get the magnitude of the vector squared. Any questions about any of this? Okay. And you might see these properties come up occasionally. Let's see, they all just kind of make sense. Sure. So let's actually work through this. So if we take a vector v, we know that it has components like this, and so on. But if we did v dotted with itself, well, that would tell us we take the first component v1 and multiply it by v1. which is v1 squared. We get the second one squared, and then we add the third one squared. With me so far? Well, if you notice, the magnitude of v is actually the square root of all these components squared. So if we square both sides of this, then the large square root cancels, and we're left with the magnitude of v squared equals to v1 squared plus v2 squared plus v3 squared, which is v dotted with itself. Make sense? Yep, no problem. Yeah, so these properties, they're all fairly straightforward, nothing too complicated about them. The thing you should really know, though, is the dot product formula. And that is this equation right here, where a vector u dotted with vector v is the magnitude of u times the magnitude of v times cosine of theta, where theta is the angle between two vectors. And this is pretty important because it lets us do several things. It lets us find the angle between any two vectors. It's also really helpful in a whole lot of different proofs. But for now, we'll go ahead and start with an example. Let's say we have two vectors and we want to find the angle between them. And I'm just going to use two-dimensional vectors because it's a bit simpler in this case. Well, our formula tells us that u dotted with v should equal the magnitude of u times the magnitude of v times the cosine of theta, and we are looking for this theta right here. So all we need to do is find u dot v. That's easy. We just take 1 and multiply it by -2. So -2, then we add 2 times 3, which is 6, and we get +4. Next, we need the magnitude of u. And to do that, we use the Pythagorean theorem. So 1 squared plus 2 squared, and we get the square root of 5. We also need the magnitude of v. That's the square root of -2 squared plus 3 squared. So that's 4 plus 9. That's the square root of 13. So then we just take all of this and plug it into our formula. 4 is u dot v. We have the square root of 5 times the square root of 13 times cosine of theta. Then we just isolate theta, so we do get 4 divided by the square root of 65. And I got square root of 65 because I multiplied these two together. That gets square root of 65. That is equal to the cosine of theta. So our angle theta is the inverse cosine of 4 over the square root of 65. Make sense? Cool. In this case, yeah, it doesn't come out as a nice angle. Um, if your professor asked it, um, depends on whether or not he lets you use calculators. If it's a unit circle value, you definitely want to give the actual angle, but this isn't on the unit circle. If your professor lets you use calculators, you might want to plug it into the calculator, but in this case, I don't care to plug it into the calculator, so all right. How about a few practice problems? These are pretty simple and straightforward. Just find the dot product of these two vectors. Um, let's see. And just put your answer out in chat whenever you come up with it, or any of them. Is the dot product of two parallel unit vectors the magnitude squared? Yes, but can you give me a single number as your answer? Think, what's the magnitude of a unit vector? Yeah, so it would be 1. Nice. Um, have you guys worked out answers for A, B, and C? Is A going to be 18? Yes, yes it is. And remember, that's because just multiply them pairwise. So negative 2 times 1 is negative 2. Then 0 times 3 is 0. And then we have 4 times 5, which is 20. So negative 2 plus 0 plus 20, of course, gives us 18. Has anyone gotten any answers for part B? E2.5 and 2. Oh, is that 21? Sorry, I didn't. But 21 halves is, I believe, correct. And 21 root 2 over 2. All right, let's take a quick look at this. So you remember we have our handy dandy dot product formula. In this case, the cosine of theta is really the only thing that's going to change. So the magnitude of u times the magnitude of v is 21. So the cosine of pi over 3 is equal to, yes, that would be 1/2. So then we would have 21 over 2 for part 1. But then for part 2, I think you might have messed up just a smidge. Remember, the cosine of pi over 2 is actually equal to 0. So for part 2, the dot product would actually be 0. Remember, pi over 2 is right at the top of our unit circle, and that means that our distance from the x-axis is, from the y-axis is 0, so the x component is 0. It's all good. Also, one other thing, you put 21 root 2 over 2. That is exactly correct if it's pi over 4. One thing that some of you might be happy to learn is we don't really care too much about rationalizing anymore, so this is also just as fine if you want to think of it that way. Just 21 over the square root of 2. All right, did anyone get an answer for part C? Right, 16. Um, if you'll remember, a vector dotted with itself is the magnitude of the vector squared. Um, Perhaps another way to remember this is if you have a vector and another vector that is the same vector, so it would be just two vectors essentially lying right on top of each other, the angle between them is 0. So if we did v dotted with v, that's the magnitude of v times the magnitude of v times the cosine of 0. But the cosine of 0 is just 1. So that is the magnitude of v squared. And of course, the magnitude of v is 4, so 4 squared gives us 16. All right. The dot product of two unit vectors that are parallel, let's see, you answered this earlier. For two parallel unit vectors, it will be 1. And again, that's kind of like the same principle as in part C. They're going in the same direction, so the angle between them is 0. Since they each have a magnitude of 1, 1 squared is just 1. What about for perpendicular unit vectors? Zero, right. And again, this goes back to the angle between them. If they're perpendicular, that means that the angle between them is pi over 2. The cosine of pi over 2 is equal to 0. So that makes that whole right-hand side of our dot product formula equal to, that makes it all equal to 0. So, in fact, any two vectors that are perpendicular will have a dot product of 0. They don't necessarily have to be unit vectors. They could be the biggest vectors you've ever seen, and as long as they were perpendicular, their dot product would be 0. So that's a really helpful application of the dot product. It lets you really quickly tell if two vectors are perpendicular, because if you take the dot product and you get 0, well, that tells you that one of your vectors is either 0 or vectors are perpendicular. So if you take the dot product of two vectors and neither of them are the 0 vector, you know your vectors have to be perpendicular. Any questions? Okay, we will move on to vector projections, which use the dot product. So let's say you have two vectors. Here's vector u, and here's vector v. And you are looking for the part of vector u that is going in the same direction as vector v. Or in other words, you are looking for what is essentially this vector. How much of u is going in the same direction of vector v? This is called projection of u onto vector v. And it's kind of a weird way to write it, but this is the projection of vector u onto vector v. And that represents the part of u that is going in the same direction as v. And let's see, the way we find this is first we need to find out how much vector u is going in the same direction as vector v, and then we essentially multiply it by a unit vector. going in the same direction as v. The formula you might see frequently is projection of u onto v is the u dot v over the magnitude of v squared times vector v. And just looking at this, it doesn't really make much sense. So I'm going to break it down a bit more. This is equal to u dotted with v over the magnitude of v times v over the magnitude of v. All I did here is I just moved one of the magnitude of v's in the denominator over to be under this vector v here. Well, if you recall, v divided by the magnitude of v is a unit vector in the direction of v. And a unit vector in the direction of v is going to be parallel to v. So that tells us the direction of this projection vector here. Now all we need to know is the magnitude of this projection vector, because a vector is comprised of two things, a magnitude and a direction. Well, the magnitude actually comes from this portion right here. And this actually comes from our dot product formula. If you divide both sides by the magnitude of v. Because then you're left with u dot v over magnitude of v is equal to the magnitude of u times the cosine of theta. And if we actually drew our vectors out as a triangle, a right triangle, this would be u, v would be something like this, but we can make a right triangle like so. Here's our angle between them. If we want to find the length of this right here, well, that would be the magnitude of u, the length of u, times the cosine of the angle. And that is where the magnitude of our projection comes from. The magnitude of u times the cosine of theta. But then we use our dot product formula to say it's equal to the dot product of u and v divided by the magnitude of v. So that's how we find the magnitude. And that is where our vector projection formula comes from. We take the magnitude of this projection vector and we multiply it by a unit vector that gives us the direction. And that gives our projection vector both a magnitude and a direction that we know are correct. That's where this projection formula comes from. With this, we can find the projection of a vector onto another vector. Any questions? We'll go through an example in a sec, don't worry. All right. Let's go ahead and do an example. Since I think if you have any questions, that might clarify things. So let's say we have u equals to 10, 24, and v equals to 3, 4. Well, if we wanted to find projection of v onto u, you could say it's v dot u over magnitude of u squared times vector u. And u dotted with v is going to be 3 times 10 plus 4 times 24. That gives us 30 plus 96, which is 126. and the magnitude of u is equal to the square root of 100 plus, oh dear, what's 24 squared? 576, which is equal to the square root of 676, which is equal to the square root of 26. Oh, sorry, that should just be 26, not the square root of 26. The easiest way to actually find the magnitude of u is it's a special right triangle. It's a 5, 12, 13 triangle, but twice as large. So the magnitude of u is 26. And our projection tells us we need to take 126 divided by the magnitude of u squared. So 126 over 26 squared times vector u, so times 10 comma 24. And essentially we get a mess. 1260 over 26 squared. I'm not going to bother simplifying this because you guys know how to simplify fractions. There you have it. That would be the projection of v onto u. Now as practice, why don't you guys find the projection of u onto v? So the other way around. Think y'all can do that? Cool. Give it a shot. 378 over 25, comma 504 over 25. Yes, I believe that's correct. And just in case anyone hasn't gotten it, we'll go ahead and work that out really quick. We've already found the dot product, it was 126. So all we really need to find is the magnitude of vector v. Since it's a 3, 4, 5 triangle, we know that it's 5. So the projection would be v dot u, magnitude of v squared, times vector v. So we have 126 over 25 times vector v. And like you said, that gives 378 over 25, comma 504 over 25. Exactly right. All right. One last note about vector projections. You go back to this original diagram. Sometimes you'll see this blue part, the projection of u onto v labeled W1. There's also a complementary part, which is the part of u that is not in the same direction as v. You might see this as referred to as W2. And the second part is equal to vector u minus the projection of u onto v. And W1 is, of course, equal to the projection of u onto v. And that's just a bit of terminology you might see. You might see this perpendicular vector right here. You just might see that occasionally. All right. We have a bit of time left, so there's one last question. Let's say you have a triangle. That's not how you spell triangle. Let's say you have a triangle and it has vertices at 3 points. 1, comma 1, 4, comma 3, and negative 1, comma 4. Is it right, obtuse, or acute? And why? That's cool. Thanks for coming and enjoy your lab session. Is it right? I actually haven't worked through it yet. So let's go ahead and start looking through it. How did you try to solve this? Sure, go ahead.
Uh,
Actually, I'm not sure. Oh yeah, go ahead.
so what I did was I just used that formula where we said the dot
Mm-hmm.
product equals the two magnitudes times cosine theta.
Mm-hmm.
And then first I took the vertexes and I found the vectors in between them. So like the first one was like between the first two, so 3, 2. And the next one was like
Mm-hmm.
negative 5, 1. And the last one was negative 2, 3. And then I just did the formula for each one. And then I found that after I did two of them, I found two with angles that are the same.
Okay. With angles that are the same. You say angles that are the same.
Actually, hold up. Hey, I don't think I did it right.
That's all right. But looking at it, you are correct. It is a right triangle. But maybe your process was a bit wrong. You said you used the formula u dot v equals to magnitude of u, magnitude of v, cosine of theta. And that's exactly right. You do want to be using this formula. Um, I went ahead and found these two vectors coming from this point 1, comma 1 and going to the other 2 points. And if we take the dot product of those two vectors, we get 3 times negative 2 plus 2 times 3. That gives us negative 6 plus positive 6, which is 0. Now, if you'll recall, the dot product of two vectors is 0 if either one of the vectors is the 0 vector or the vectors are perpendicular. So in this case, neither of these vectors is the 0 vector, so that tells us that the angle between them has to be 90 degrees. Because the angle between them is 90 degrees, it has to be a right triangle. Um, if it were instead an obtuse triangle, then what we would look for is a vector pair where both vectors are coming from the same point. So for instance, when we take the dot product, we would want to look at vectors either that all come from the same point. So we could look at the vectors coming from the second point to here and going to there. That could be a different vector. Or again, we could look at vectors going from this third point down to here. It's important that we get the vectors originating from the same point, because otherwise it's going to flip some signs, and it's a lot faster to actually determine the angle between these two vectors. That should be in blue in the color system. Because if you'll recall, the cosine of theta is bigger than 0 if theta is smaller than pi over 2 first, which is 90 degrees. And that would tell us that it has the potential to be an acute triangle. The cosine of theta is equal to 0 if theta is exactly equal to pi over 2. So that would tell us that, like we had in this case, we have a right triangle. The cosine of theta is smaller than 0 if theta is bigger than pi over 2. And this would tell us that we have an obtuse triangle, because of course we can only have one obtuse angle in a triangle at a time. So if your dot product is equal to if you get a dot product that's smaller than 0 and both the vectors originate from the same point, that tells you it's an obtuse angle, so you have an obtuse triangle. One thing to note, if it's an acute triangle, you have to check all three vector pairs, all three angles, because you can have two acute angles on an obtuse triangle. But if you just check those two angles and say, oh, they're both acute, that's still not necessarily enough to determine whether it's an acute triangle, unless you actually found the numerical values of those angles. This way, you can just check the signs. If the dot product is less than 0, then you know it's an obtuse triangle. If it's equal to 0, you know it's a right triangle. So it's just a bit faster than finding all three, than actually finding the exact angles in those cases. Any questions?